All right. Thanks for invitation, and I'm not Anyudha, so you will have to bear with me for a couple of lectures today. Right. So yeah, it was hastily prepared because I was sort of notified in the very last moment, but I hope it will be more or less coherent. Please stop me anytime. I'll try to move relatively fast, but don't hesitate to slow me down. So I'm going to tell you about particular aspects which fascinates me, namely fluctuations in systems where you cannot define quasiparticles. Fluctuations as opposed to mean field behavior. And I'll hope to explain what is mean field and how you think about mean field, which is interesting by itself, but then there is a whole other layer of an interesting physics which is due to fluctuations in these systems. And that's what I will try to explain you in a couple of examples. And most of what I will tell you, I learned from these two gentlemen who are in Cologne, and it's published some time ago. All right. So SYK. Why to think about SYK? Well, for me, first of all, it's a cute, exactly solvable model, which is always fun in physics, in theoretical physics at least. So I will try to explain you why is it exactly solvable, and there is more than one sense in which this model is exactly solvable. And I'm trying to give you at least two of them, but there are more actually. Well, then it has these tantalizing relations to holography, gravitations, which possibly can teach us something, or maybe can teach gravitational people something new. I will mention it quite briefly. It's not my main expertise, but if you have questions, I may try to delve more on it. And then finally, another reason to think about it is that it, after all, may have something to do with real matter. So we can try to build some more realistic material models out of SYK, which probably Senke already started to discuss. I will also have something to say about it, hopefully. All right. So I will tell you about these fluctuations, which come with this slightly mysterious name Schwarzschild field theory, and then we'll see how it goes. All right, so the model is this. You say that you're primarily interested in the physics of electron-electron interactions, unabstracted by some other phenomena like kinetic energy. So then the idea is, why not to start from a Hamiltonian which has just interactions and nothing else? Okay? So namely, I don't have kinetic energy. I have only 4 fermion terms. In this case, I used Majorana fermions, but that's not really crucial. It's easier in some sense once you get used to it. But we will talk about complex fermions as well. Now, so this model only makes sense if you say something intelligent about this matrix element, which is huge tensor with 4 indices. And unfortunately, nobody can say, at least I certainly cannot say anything intelligent about it. And then the nice thing which comes from this gentleman is, let's just, if we cannot say anything intelligent, let's just assume it's random. Okay? So random in the sense that we'll say that mean value is 0, and then there is a Gaussian distribution where all matrix elements up to symmetric permutations I assume to be independent, and with a variance which is called J square, and that's the only energy scale in my problem with capital J. And it's convenient to scale it with n cubed. You will see why is it a convenient scaling. Okay, but that's just convention. There is no physics in it. What else should I say about it? No, well, probably good. Any questions? Yes?
Is there a reason why we're taking the mean to be 0?
No. But look, if it is a constant, right, then you can introduce sum of all chi as a collective variable, right? So then you will have this collective variable times power 4. So it's an interesting addition to the Hamiltonian, but it's almost trivial. It's not completely trivial, but almost. So you can do it, but it will not change physics much. All right. Yeah, you can do it with complex fermions pretty much in the same way. Then you have a freedom to introduce chemical potential. And then there is a choice where you call this guy with random matrix J, whether you take it out of real or complex ensemble of numbers. And that may play a difference. But I may talk about it later a little bit, but just for now, have it in mind. All right. So for the history, as you can guess from the name of the model, it was suggested by Baigas and Flores in 1970, and these two guys in the same year. But then it was firmly forgotten. Yeah, they are all nuclear physicists, and they were interested sort of in extended Wigner-Dyson random matrix thinking, but not for kinetic kind of energy, but for interactions. So what they did back in the time, they did numerics, and they understood quite a bit about random matrix kind of aspects of the model, but not at all the short time behavior, which we will mostly talk about. So I'll explain what I mean. And then, of course, came Subir in 92, and he was motivated also by completely different. He didn't know about these nuclear physics people, and he was thinking about random magnets. And then Kitaev came in 2015 and made these connections to gravity, and that's how this hype started. All right. So few sort of simple remarks. So if you have n fermions, or Majorana fermions, doesn't matter for a sec, you can always go to the basis of occupation numbers, occupied or empty. So you will have a huge Hilbert space with a dimensionality 2 to the power, if it's Majorana, 2 to the power n over 2. If it's fermions, then it's just 2 to the power n. And you can write your Hamiltonian as this very big, exponentially large matrix, right? And it will be a random matrix because my matrix elements are taken from random Gaussian distribution. But it's not a usual random matrix because it's extremely sparse. If you think carefully, then you have a matrix with the size 2 to the power n over 2 times 2 to the power n over 2. But in each line of this matrix, or in each column of this matrix, you have only n to the power 4 non-zero matrix elements. Because that's how many possibilities you have to annihilate two fermions and to create two other fermions. So it is exponentially sparse. But its position of these sparse non-zero elements are not at all random. It is quite correlated. Okay? So it's a random sparse matrix with correlated position of non-zero matrix elements. Okay? All right, so you can give it to a computer and you can ask computer to diagonalize it if n is not too big. So this is for 32. Nowadays people go to 36, maybe even 38. So this is a density of states of many body levels. So there are that many levels, and they're just a histogram. So if not for interactions, they all would be degenerated 0, because then my Hamiltonian will be 0. And now there is these interactions, which are sparse random non-zero matrix element. They create level repulsions. They repel each other, and that's what you got. So sort of semicircle, although that's just finite size effect. in reality, it's more like Gaussian and not like a semicircle. Yes?
Is there any averaging to make this picture? Or is it
No, that's, as far as I know, just single realization. And if you take any other realization, you pretty much get the same. So that's a good point. All what we know about pure SYK tells us that it's very well self-averaging model. There is no any glossiness. There is nothing like that. Okay? It doesn't mean that it's always the case. Maybe some deformation of SYK behave differently, but pure SYK is like this. Now, one thing to mention is that unlike usual Wigner-Dyson physics, where we say let's put chemical potential around middle of the band, and let's focus on the physics right here. Here we don't have this luxury, because this is a many-body energy levels. So the many-body ground state is very last energy level here. And the low energy physics is entirely sitting right here. So from the point of view of low energy physics, 99% of the spectrum is sort of completely irrelevant, and all what you care about is this corner. Okay, and in this corner there is again well-defined density of states. Again, I think it's a single realization. So there is an envelope which is well understood. It's actually a theoretical curve with one fitting parameter. So we think we sort of understand at least density of states. Yep.
Does this density of state look like root E or something, or different than that? Because
yes. So this curve is hyperbolic sine of root E. So it's very smallest E. It is just a root like Wigner-Dyson, and then it grows exponentially as it should in many body system according to beta or whatever old time arguments. Okay. Now, again, in case you're interested, you can start doing level statistics, namely distribution of nearest neighbors, nearest spacings, and you will discover pretty soon that it is perfectly Wigner-Dyson, absolutely perfectly Wigner-Dyson. So this is an old data. By now they have much better data, and they don't even have these tiny deviations at 10 to the minus 4. So it's really perfect Wigner-Dyson. Nobody knows quite why, but that's the case. Experimental fact. Okay. Very good. Yes, you can even look for statistics between ground state and the first excited state. You need many realizations for this, but you can do it, and you again find pretty much perfect Wigner-Dyson. Okay. Again, nobody knows why, but experimental fact. Yeah.
And the Hamiltonian right now is still just the SYK model.
Right, just SYK model, nothing else.
Nothing else.
Yeah. And then there is an interesting story, what kind of Wigner-Dyson you have, and the fact is that it may be any of them, it's actually maybe any of the 10 different ensembles, depending on parity of this capital N, modular 8, and depending on what, okay, in the first approximation, that's what's important. All right. Now, the big picture is like this. So if you think about time scales, or alternatively energy scales, but time is probably a little bit more physical variable, there is the only scale, capital J, which give you dimensionless parameter. But then there is a zoo of time scales which are associated with this capital N. Okay? So there is a time scale which in these units is 1, which plays a role of UV cutoff. I will explain in a sec what it is. Then there is a so-called Ehrenfest time, which scales logarithmically. There is another time which I will sort of talk quite a bit about, which scales like n. And finally, there is a Heisenberg time, which scales like e to the power n, or 2 to the power n, whatever. And it's there where you see Wigner-Dyson physics. Now, at an Ehrenfest time, you see completely different phenomena, which is basically classical. So this is deeply quantum regime. This is practically classical regime, where you have exponentially, where you see exponential growths of certain correlation functions, which people like to call out of time order correlation functions. And it's both interesting and fascinating phenomena, completely different. But I'm not going to talk about none of them unless you push me. And I want to talk to focus somewhere in between, where the physics is sort of semi-classical. It's not classical, and it's yet not very deeply quantum. And there are wealth of interesting sort of collective phenomena which takes place there, and that's what I will talk about. Okay? So far, so good? Okay. Right, so by the way, that's good enough as long as n is finite, but this inequality is fulfilled, which is not too hard to arrange. As
give us some qualitative picture of what happens on our Heisenberg time.
Well,
Besides being back to Wigner Dyson, what happens with the correlation function?
well, so again, at the very longest time, it's perfectly Wigner Dyson, whatever you know from conventional random matrix theory. But then there are shorter times, somewhere here in between, which you can associate with sort of Taoist times, where you start seeing deviations from random matrix theory. They probably still scales like exponential, but slightly smaller than that. And there is some phenomenology which takes place there. People understand a little bit of it, but we can talk separately about it.
Is the n over 2 roughly the inverse of that, the level spacing?
Precisely, yes. That's a many-body level spacing. Right, so that's where you start seeing these oscillations associated with discreteness of many-body spectrum. Okay?
And when you say weak field theory, the control parameter is n?
Yes, n is definitely control parameter. All right, so since you mentioned it, let me very briefly tell you how you built this field theory to begin with. So what you start with, you look at your evolution operator, or exponent in your functional integral, imaginary time functional integral, which contains SYK Hamiltonian, which has this random coupling. So now you want to average this over realizations of your randomness. Now, strictly speaking, to do it in a clean, nice way, you need to introduce replica, because you know that what you're actually supposed to average is a logarithm of the partition function, is not a partition function itself, right? So just to be pseudo-rigorous, I put here a replica index which run from 1 to capital R, and then in the end of the day, you need to put this capital R to 0. But it will not play a significant role. Okay, so if you do that, and you average over your random J, I, J, K, L, you got a combination of, you do Gaussian integral, and you got a combination of 8 fermionic operators. Okay? I think you can believe me. So then you can compactly write down these 8 fermionic operators. If you introduce this object, you can call it green function, but it's not an expectation value. It's just a product of 2 fermionic fields. So it's a composite, non-local in time and non-local in replica space bosonic object, at least commuting object. And then this object is written as this matrix G, element by element taken to the power 4. That's my 8 fermionic operators. Okay? And then the trick is to let know your field theory you want to let it know that you are so smart that you introduce this notation. Okay? So how do you let your field theory know that you're smart? You stick 1 into your partition function. But you write this 1 in a clever way. You say that that's an integral of a delta function, and this delta function is nothing else but this object. And you integrate over all g. Okay? So that's 1. Since I have just delta function with unit Jacobian, I integrate it and I get 1. And then you're getting even smarter. You say that let me write this delta function as an exponent. And then you need another matrix field, sort of canonically conjugated to field G, which you call sigma. And you will see in a moment why sigma is a good notation. So and then this one takes a form of exponent where you have this sigma times G, and you have sigma times bilinear combination in your fermions. Okay? So then, if you think a sec, interaction term is now written entirely in terms of this G, so this is basically the only place where my initial fermions show up. And now you can integrate them out, and you get a determinant, or actually phi-n, because that's Majorana. So in the end of the day, you end up with so-called G sigma action, which has this 3 parts. One is coming from your phi-n, or fermionic determinant, which has dt, like always in field theory. You have psi dt psi. Self-energy, which is just coming from here. Sigma, I shouldn't call it self-energy, but I will call it self-energy in a sec. So there is this matrix field sigma, which is coupled to 2 fermions. So no surprise that it shows up inside this phi-n. Then you have this g to the power 4, which come from your SYK interaction. And finally, you have this sigma times g piece, which is coming from delta function. So since this g was sitting in a delta function, that's here. Is it okay that I'm doing it like this? I was going to do it on a blackboard, but then blackboard is sort of crappy. Could you live with this? No, okay. Since nobody object, I will go on. So now the important thing to notice is that there is this capital N sticking in front of my action, and there is no any other place where I have capital N. And to have this property, it's important to have this smart scaling of SYK interaction, like variance is j square over n cube. So that's how I chose that in the first place, and because of how they have chosen it in the first place. And because of that, there is this nice property that n sticks out of an action, so it plays a role of inverse Planck constant. Whatever is sitting in front of action is called inverse Planck constant, right? So if you go to the large n, and in the limit n to infinity, then all what you want to know is essentially saddle points of this action, because fluctuations are completely suppressed. Okay? So, right. So that's what I'm trying to say, that if you want to investigate this limit where n is infinity, then all what you need to do is to take variation of your action with respect to g and with respect to sigma. Okay? Okay, so let's do that. So if you take variation with respect to sigma, you have inverse of this guy, and you call it g. Okay? So variation with respect to sigma is inverse of this plus g equal to 0. You see it? And then you take variation with respect to g, you got g cubed is equal to sigma, or minus sigma, whatever. Right? So that's these two equations. So that's variation with respect to sigma, and this is variation with respect to g. Now you look at it and you realize immediately that this is nothing else but self-consistent Dyson equation. So the first equation is just Dyson equation as written in any textbook, nothing else. So it's sort of have no information whatsoever. The second equation is a little bit more informative, and it tells you that in this n to infinity limit, what you have to take for self-energy is just free fermionic Green functions, which self-consistent Green function, which already includes self-energy. Okay? So what you do in this way, you effectively sum up the diagrammatic series which look like this. You have this, what they call melons, and you then insert melons inside the melons, and then melons inside the melons inside the melons, and you sum up all these melons. Okay? So they call it melonic diagrammatic. Now, by the way, in case you're interested, this reddish dashed line is about the following. You have a random coupling sitting here with JIJKL, and you have a random JIJKL sitting here, and it's a Gaussian random variable, so you have to pair up with Gaussian random variables with each other. So the specific way you do the pairing is precisely like this. In each melon, you pair this with that, and then this with that, and so on and so forth. Right? So that's how your averaging proceed.
Can we see, you forgot on the draw about the replica trick. Can we see after having done this that it makes no difference?
What, replica?
Yeah.
Very good. Strictly speaking, no. So you can seriously be concerned about replica non-symmetric solutions of these equations. And people, including myself, did some investigations if these solutions indeed exist. And the answer is yes. And then if they have smaller energy, free energy, and the answers seem to be no. And if they have any relevance to numerics, which people see, which people do. And again, the answer is resoundingly no. So solutions exist, but they seem to be not reflected in any physics.
Okay. So somewhere along the way, you've taken a replica symmetric.
Right, pretty much next click of the button, I will take replica symmetric and replica diagonal solution of that. Okay? And again, in this case, that seemed to be, by variety of indications, seemed to be a kosher thing to do. But again, there may be other situations where it is not. Okay? All right. So let's proceed. So it's integral differential equations. So if you, as Pierce suggested, you take a replica diagonal solution, then it's not very hard to solve numerically. And people did it with very good precision, actually. But to have some analytical understanding, we can sort of even try to simplify our life a little bit more. Namely, let me be brave for a sec, and let me forget about this time derivative. Okay? So then I have equation sigma times g, matrix multiplication is 1, and then sigma is g cubed. So you can try some scaling solution. Namely, g is a certain power of t minus t prime. Okay? What else can we try? So you try it, and in a couple of lines, you convince yourself that it works. And specific way it works is that if you take this g to be 1 over square root of t minus t prime. Okay? And sigma will be, of course, 1 over t minus t prime to the power 3/2. And then you can substitute it here, and you can convince that that's indeed works. Okay? Just by counting dimensionality, essentially. Okay? Now, since it's nothing else but counting dimensionality, you can go back and say, can I be smart in the first place without doing any calculation at all? And of course you can. Namely, you just look at your Hamiltonian and you see 4 fermions and dt integration over time in your action, not a Hamiltonian. And you immediately say, well, that means that conformal dimension of my fermionic operator in this fixed point, if it is a fixed point, should be 1/4. And if dimension is 1/4, then green function, which is 2 fermions, should have power 1/2. 1/4 times 2. So that's pretty much all the calculations you need to know. Right? So you got this green function, which in energy space look like 1 over square root of epsilon. And that's essentially exact solution, if you wish, in this limit n to infinity. Okay? What do I want to say? Well, right. So it's sort of simple, and the way I'm presenting it, it's almost for free. But it actually has lots of interesting consequences. Namely, what you discover is that instead of quasi-particle pole, remember, if not for interaction, you would have pole at epsilon equals 0, because all your energy levels are chiefly sitting at 0. Right? So you will discover that there is a pole with certain weight at epsilon equal to 0. Now you introduce interaction, it sort of changes my many-body spectrum. And what it does for single particle green function, it transforms the pole into the branch cut. Okay? Instead of having pole at 0, I now have a branch cut which emanates in a complex plane of energy from 0. So that's the point where people say, well, this is not a Fermi liquid. You don't have any remnants of quasi-particles. So many-body spectrum is, of course, well-defined, but there is no sense in which single particle excitations are any special. Okay? And then you can go and try build matter out of this non-Fermi liquid, and I think Senke should have said something about it. If not, I will comment about it later. Okay? But again, this is n to infinity limit of the model where all fluctuations are completely suppressed. In a sense, this is if you wish, a classical limit of the model. Okay? Any questions here? Yes?
So why do you, in the beginning of your talk, you called this a stable fixed point?
Well, you will have to wait probably until my second lecture to answer this question, but I promise I will. Okay, so let's proceed and start thinking a little bit more closely about fluctuations. So to do that, we need to discuss symmetries of my action, and here I write it back in fermionic way. So because it's a little bit easier to understand what is it about. Now, again, if we will be brave again and forget about this dt, then you immediately notice that this action has an exact symmetry. Namely, instead of time running uniformly from 0 to beta in a circle, you can let this time to run with arbitrarily positive speed. So you have a clock, your time goes from 0 to beta, but this clock may be crazy. It can go faster, slower, faster, slower, faster. Okay? So kind of gravitational logic where you allow your time and space, there is no space here, but at least your time, you allow to deform and do whatever. So mathematicians call these things group of this transformation is called a group of diffeomorphisms of a circle on itself. And I'll talk a little bit more why it is a group and how to understand it as a group. Okay? But for now, think about it as just a function which transforms time into something else. And then what you do with your fermionic variable, you of course stick this new function as an argument, but then you multiply it by h prime to the power 1/4. Again, why 1/4? Because I have 4 fermions sitting here. And then you immediately notice that four of these fermions give you a factor of h prime, and d tau times h prime is dh. So all what you do, you do this change of variables from tau to h, and your action is completely invariant. Okay? So that's provided, you forget about this dt, this is an exact symmetry of the model. Okay? Now, it's actually always the case in some sense if you have only 4 fermion terms or only 6 fermion terms or whatever, or only 2 fermion terms to that matter. It will be a symmetry. Why didn't we talk about this symmetry before, at least in condensed matter community, not too much? Because this idea of forgetting d tau is typically a crazy idea. And you're not doing any good to yourself if you do it. But SYK in this sense is special, in the sense that forgetting about this d tau is not completely ridiculous. Now, why not? Because, so let me mention this. So because remember, my green function was 1 over square root of t minus t prime. My sigma, which was g cube, because of this, is immediately t minus t prime to the power 3/2. So this transforms to 1 over square root of epsilon. This transforms to square root of epsilon. Do Fourier transform, and you will find it. So therefore, this construction d tau minus sigma, which is of course nothing else as I epsilon minus sigma, you see that if sigma behave like square root of epsilon, and this thing behave like epsilon, then at small epsilon, that's not a completely crazy thing to forget about this. Okay? But you needed this square root to justify it. In an older model, which we typically learn in the textbook, this is not the case, and therefore forgetting about this is not good. Okay? All right. So why am I proud of this symmetry? So before I explain what's going on, so you need to transform your green function, which is 2 fermions, and the way it transforms is like this. Now for each h, you now have this combination. So this h prime to the power 1/4 are simply remnants of this guy, and this denominator is, again, nothing else. So 2 times 1/4 is my square root.
Is there a more general reason for why you can ignore this d tau term? Is it a large number of flavors or the randomness of the interactions?
No, at least not what I know. So the best reason I know is the singular behavior of a self-energy. If you have a Fermi liquid, then self-energy typically goes to some constant, and that may be not a good idea to do. But this singularity is, well, constant probably not a good thing. It's much less than epsilon. Unless you have disorder, but disorder is a separate story. All right, so your green functions transform like this, and I can write a similar formula for sigma, for self-energy. Just instead of 1/4, I will have 3/4, of course. And then what you can check, just brute force, that this is still a solution of my self-consistent Dyson equations. Okay? So I showed you one solution, and we derived all this non-Fermi liquid and all these nice features from it. But in reality, it's not just one solution. It's entire manifold of solutions. Okay? And as long as you neglect this d tau, which we did anyway, all of them are equally good. So it's sort of almost zero mode in your theory. Okay? So now d tau, of course, breaks this degeneracy, and it provides some cost for transformations h of tau. Not any transformation is now equally good. But this cost is very small in the sense that it comes from this epsilon, and since epsilon is a small correction to everything else, this is a very mild cost which these transformations cost you. Okay? Now, of course, the best one is just h of tau equal tau. Okay? So our old solution, where we didn't think about reparameterizations at all, was actually the best from the point of view of the d tau. Okay? But now I have to think that, okay, others are also exist. They slightly worse. They cost me a little bit of action, but a little bit. So I need to find a way to take them into account. Okay? Clear? No, right. So then, before I tell you how to take them into account, I need to tell you a little bit more about symmetries. Namely, if you look at this green function, you realize that not any transformation h will transform my green function. In particular, there is a subgroup of this big group GFS1 which does not change green function. Namely, you can try an exercise, take this h function as a fractional linear function of time, a tau plus b, c tau plus d, and stick it into this expression, or ask Mathematica to do it. And you will find that nothing depends on a, b, c, d. So you will be back to your old green function, which you already know. Well, okay, good. So that's what I talked about. So you need to think about these transformations as a group. So if you have a transformation G and you have a transformation H, then a combination of two transformations should be understood as G as a function of H as a function of tau. Okay? Or H times G will be H as a function of G as a function of tau. Right? And then what this thing tells you is that if you take this G of a special form, fractional linear form, then there is this invariance. Okay? So the simplest way to see it is just take H to be tau, right? So take H to be just tau, flat reparameterization, and stick it here, and you will find that what I said. Nothing changes. Okay? Now, these transformations of this form form a subgroup of a general group, of a big group GFS1, which is called SL2R. Now, why is it called SL2R? Because if you take two of such transformations, oops. What?
There's three below you. Turn it around.
Oh my God. You would think Magnetic Lab can do better. So black is not good. Right. So if you have transformation G equal A1 tau plus B1 A2 C2 tau C1 tau plus D1. And then you have another transformation H, which is A2 tau plus B2 C2 tau plus D2. And now you want to look what is G of H of tau, right? So you take G, you substitute here H, and now for H, you substitute your transformation. So 2 lines of algebra will convince you that you will have a fractional linear transformation again, A3 tau plus B3, C3 tau plus D3, and then A3, B3, C3, D is ABCD1 times ABCD2. So subsequent transformations of that sort completely isomorphic to multiplication of 2 by 2 matrices with this ABCD coefficients. So this is this is linear group of 2-dimensional real matrices. And then you can notice that determinant doesn't matter because it's anyway ratio. So you take these matrices with unit determinant. So it's a 3-parameter group of this transformation. So more generally, so this DFS1, if you think about algebra of DFS1, it's given by the Virasoro algebra LM, where m is from minus infinity up to plus infinity, and that's more or less generators like e to the I m tau over beta d tau, and they form Virasoro algebra LM Ln. Commutator is m minus n Lm plus n. And then you can notice that there is a subgroup of this algebra L minus 1, L0, and L1, 3-parameter subgroup. You can see with a naked eye that they indeed form a subgroup. And this subgroup is precisely this SL to R. And what I'm explaining here is that SL to R does not lead to valid transformations of your field. And that means that your low energy degrees of freedom are actually living in this symmetric space, coset space of DFS1 slash SL to R. Okay? That may look like an algebraic detail, but it is actually important. Okay?
Could you go back to the previous slide?
Oops. This one?
Yeah. So when you have this symmetry, that means energy is not conserved.
Energy is not conserved. Well,
Because if the transformation can be nonlinear.
transformation is nonlinear, yes.
So, and that breaks the translation.
In time, yeah,
So
yes.
it breaks.
Yeah.
So and okay. Another question is, what is conserved in this case?
Action,
Action is conserved.
right. And you can
Oh yeah.
you can just see it with a naked eye.
So what does that mean when action is conserved?
Well, isn't it how we think about symmetries in field theory?
Of energy conservation.
Right, yeah.
Energy is still conserved. It's still global time translation is still symmetry.
Global time is still.
So subgroup, yes. So energy is still conserved.
Well, there is a Hamiltonian initially, of course. I mean, when you calculate your observables, energy is a good quantum number, but we're talking about sort of looking on fluctuations.
Besides energy, there are more conserved quantities. That's the thing.
Okay. So this is additional.
Conserved quantities.
Right. Yes, this is additional conserved quantity. That's why I'm saying it's exactly solvable model in some sense. Right. So what I'm trying to explain with all these words is that the actual small energy degrees of freedom are orbits of small group SL to R within large group as diff S1. I think mathematicians call them coadjoint orbits. All right. So now the next question is what is the corresponding action? And again, what I told you is that if you forget about d tau, then the action is just zero. Any reparametrization of time is as good as any other. But if you remember about d tau, then that's not the case, and there is a corresponding action. And here is how it looks like. It's very simple. There is some constant. I'll explain in a sec what it is. More or less it's written. And then there is this object, which is called Schwarzian derivative. Okay? And mathematicians know this object since mid-19th century. And it pops up in many branches of mathematics. And here it's operational definition. It's third derivative divided by first derivative, and then minus 3/2 second derivative divided square. Okay. So now if it's first time you see this object, you would probably think that I'm crazy. And physics cannot be that complicated, right? Why on earth anyone would think about this construction? But it's true, and I'll try to convince you that it's indeed a valid construction which is worth thinking about. Now, why does it appear in this case? Because this is a simplest possible differential operator which is invariant with respect to this group SL to R. Namely, you take your Möbius transformation, you calculate Schwarzian derivative of the Möbius transformation, and it is 0 for any A, B, C, D. Okay? And mathematicians make sure that there is no anything simpler than that which will have this property. Okay? Or slightly more general, superpositions of element G and H, its Schwarzian derivative is the same as derivative of H. So that's this invariance. Now, if you think back on what my degree of freedom that we live in this coset space, diff S1 / SL to R, you immediately realize that my action must have this property of invariance with respect to SL to R. Because SL to R transformations are not actual transformation. They cannot cost any action because they do not change my field variables. Okay? So I need an object which will have this property. But, and that's the simplest local differential operator. That still doesn't mean that action has this form. For example, action could be non-local, maybe even more crazy than this. But certainly this is the simplest local action having this invariance property you can imagine. Okay? And then you can do some algebra and convince yourself that it's indeed true. That under very reasonable sort of assumptions, your time derivative indeed leads to this action. I can explain privately how it works. And then very soon, I don't know, maybe this lecture, maybe next one, I'll try to explain you that there is a way to look at it which makes it much less crazy than this. There is a simple transformation which brings it to very nice and acceptable for physicists form. Okay? Any questions? By the way, when am I supposed to shut up?
Well, you have an hour, so you started at 10, so in about 8 minutes.
8 minutes, okay. Very good.
But if you want more time for questions, you can stop it.
Okay. So, all right, okay. So maybe I will waste my 8 minutes on that. So that's precisely the point when this type of an action appear, but that's the point where gravitational people jump. Yeah.
I think the title is like is Coldstone action. Then the H is, I think H is just the parameterization is the differential. Then what is the Coldstone action? Coldstone action.
Sorry, I'm deaf on one ear, so.
Your title is Coldstone action. Coldstone.
Goldstone.
Yeah. Then what
Oh.
is the
Well, yeah, ignore it. Well, look, if you think about magnetic analogy, right? So you have group of three, and then you break your symmetry. You choose magnetization. You break it down to O2, and then your Goldstone mode manifold is O3/O2, which is two-dimensional sphere. So your Goldstone modes are parameterized by angles on a two-dimensional sphere, right? So that's very similar construction. So you initially have group S1. You break it sort of explicitly with this time derivative, but you break it not completely. You break it down to SL2R. So your manifold of soft modes should be parameterized by this quotient construction. So in that sense, it reminds you terminology of the Goldstone modes. But one can argue that this is not a good terminology. Thanks. No, right. So once this Schwarzschild appear, gravitational people start to be sort of excited because they know this construction for quite a while since so initial theory was in 83 and 85, but then slightly later in early 90s, they realized that there is a Schwarzschild in this theory. So that's a theory of two-dimensional gravity. And it is called Jacquier-Teitelbaum. Now, why do you need these names? Why Einstein is not enough? Because if you take just Einstein, so that's pretty much the first term here. If you ignore this phi naught, that's what Einstein told us to do. But then in 2 dimension, you immediately realize that R is just a topological invariant. So it's a constant in 2 dimensions. So there is no dynamical degrees of freedom whatsoever. And then they say, well, that's not too good, so let's introduce gravitational constant. Let's allow it to be a field. So here it is called field phi. Okay, so if gravitational constant is an additional scalar field, then you have slightly more sort of degrees of freedom to play. And they call it dilaton. So that's this overall scale, which in case of Einstein is just a constant. Now you allow it to be dynamic variable. But that doesn't give you too much of leverage because, look, since you stick it linearly in your action, you integrate over this phi, you get a delta function of whatever is sitting here. So that means that you get a fixed geometry, 2-dimensional geometry of constant, and in this case, constant negative -2 curvature, okay, which is nothing else but Lobachevsky plane, hyperbolic plane. So when I was in school, they draw pictures like this for the Lobachevsky plane. But then you can introduce smart parameterization of this Lobachevsky plane, and you map it onto a circle with finite radius. But when distances within this circle goes like scale of these beds or whatever. So you can go to internet and you will find this circle populated with any kind of animals, I guarantee. There are fishes and mermaids and whatever. And then you call it with bombastic name ADS2 gravity, right? But it's still the same hyperbolic plane. So it's almost dead. But then what we realized that there is still a little bit of dynamical degree of freedom left, namely this field living at the boundary. Okay, so the boundary value of this field is still dynamic, and you can reduce it to a certain effective field theory of this scalar field at the boundary. And then, oh miracle, by some reason, the action of this scalar field at the boundary happens to be exactly the same Schwarzian if you write it in the proper variables. Okay, so the claim is that dilaton field at the boundary is governed by the Schwarzian action, pretty much the same as we get for SYK. Okay, and that makes gravitational people to be excited, and then they found more exciting parallels between the two models, but that's as much as I was going to go into this business. Okay. All right. So now, well, probably it's a good place to shut up and take some questions.
So in this correspondence of a quantum mechanical system and a gravitational theory, here you have not a quantum mechanical system, but one that's now being averaged over disorder. But it seems that you still have a normal gravitational theory without anything that looks like averaging. How do they think about that?
Yeah, that's a very good question. I'm not sure how they think about it. Right? So I'm probably not a good spokesman for them. Now, you can build a similar theories which do not have any randomness. They sort of go by the name tensor network models. So it's a similar construction, at least the equivalent on a level of a mean field. Right? And then you don't have any averaging. You just have some very well-defined rules of the game. So your matrix is not random. It has, if you wish, ones and minus ones in a specific. Now, whether there is a correspondence on a level of fluctuations beyond the mean field, whether they have this Schwarzian physics, these tensor network models or not, nobody could explain to me, at least, in a reasonable way. And I talked to people who invented them, so they seem not to know about it. So therefore, I don't quite know how important is this randomness and averaging and all that. So it's a